Coulomb's law. If two objects have electrical charges Q1 and Q2, and if they're separated by a distance r, then Coulomb's law says that the electrical or coulombic force between these objects is kq1 q2 over r squared. K, which you write here as k sub e, e for electrical, is a constant, approximately equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. Now, matter can be electrically charged. Charges can be positive, negative, or neutral. If an object is neutral, it has zero electrical charge. Here's the representation we'll use for a positive charge, a negative charge, and a neutral charge. Coulomb's law says that like charges, that is, charges with the same sign, repel each other, while opposite charges attract. If we put two positive charges close together, they'll repel each other since they have the same sign. The same goes for two negative charges. If a positive and a negative charge are near each other, they'll attract. And neutral charges won't interact with electrically charged objects. Now, the closer two charges are, the stronger the force between them will be. So let's return to our positive and negative charges. When they're far apart, like we showed them here, the force between them is relatively weak, as indicated by the short arrows. As we move the charges closer together, the forces get stronger, which we show by the arrows getting longer. Coulomb's law is also quantitative. It relates the force between two objects to their electrical charges. Here's Coulomb's law again. The force is equal to K times Q1 times Q2 over R squared, where Q1 and Q2 are the charges and R is the distance between them. One of the keys to Coulomb's law is that the charges are multiplied together, which means their signs, whether positive, negative, or neutral, also get multiplied. Let's say Q1 is positive, and let's say Q2 is positive as well. Multiplying two positive charges results in a positive force. And when a force is positive, here it means repulsive, pushing the charges away from each other. Now let's suppose Q1 is negative, and that Q2 is also negative. Multiplying two negatives again results in a positive force. So again, Q1 and Q2 will repel. If one of the charges is positive while the other is negative, then their product will also be negative, which means the force is attractive. And finally, if at least one of the charges is neutral, meaning it has zero electrical charge, this zero carries through in the multiplication, and the force between them is zero. So multiplying the charges is one key to Coulomb's law. The other key is the r squared in the denominator. Suppose we double the distance between two charges. How would the force change? Doubling the distance means we're changing the r to 2r. Squaring 2r gives 4r squared, and we can move the 4 in front of the fraction, keeping it in the denominator. So now we have 1/4 of our original force, back when the distance was r. Doubling the distance results in 1/4 of the force. Similarly, having the distance would have quadrupled the force. In other words, Coulomb's law is what's known as an inverse square law, like the law of gravity, and so distances are very important. Finally, just a little housekeeping, but not critical to understanding Coulomb's law. We've thrown around this number K, 9 times 10 to the 9 Newton meter squared per Coulomb squared. Another way to write K is 1 over 4 pi epsilon naught, where pi is the numerical constant, 3.14159, etc., and epsilon naught is what's known as the vacuum permittivity, also known as the permittivity of free space, and it's approximately equal to 8.85
let's take our time tonight, girl. Above us all the stars are watching. There's no place I'd rather be in this world. Your eyes are where I'm lost.